Hi everyone. In this session, we are going to discuss about natural, damp and free vibration. So first we will start with natural vibration. So we know that the sound is always produced due to the vibration of a body or a material, right? Okay. So natural vibration, how can we define natural vibration? We can define the natural vibration as it is a periodic vibration produced by a body in the absence of any external force. Or we used to call this natural vibration with another name, that is free vibration. Okay. So just imagine that I have something is hanging here, and if I make a disturbance to this body, what's going to happen? It's going to oscillate it. Okay. So initially the body start vibrating with its own natural frequency. Okay. But in normal condition, see the way how it vibrates. Initially it has a long amplitude. Now slowly as the time goes on, the amplitude is getting reduced, right? So here there is a presence of some external force, that is a resistive force applied by the air friction or fluid friction. Okay. So that is what it is mentioned, that it is a periodic vibration produced by a body in the absence of any external force. So natural vibration is only possible in vacuum. In normal situation, it is not at all possible. Okay. The vibration produced by the body is known as natural vibration. Same way the time period. The time period of the body depends upon the size and shape, or we can tell that the structure of the body. Okay. So the time period depends upon the structure of the body. The time period of the natural vibration is known as natural period, and at the same way the frequency of the natural vibration is known as natural frequency. And this natural frequency and natural vibration, all these vibrations are possible only in vacuum. Okay. Now let us see some examples of natural or free vibration with the condition that it has to be considered in vacuum. Otherwise, the resistive force will be acting. So we are going to discuss that with the condition if it is in vacuum, how it is going to affect it. Okay. So first one, consider the case of a simple pendulum. Simple pendulum. You know what is a simple pendulum, right? Simple pendulum. So simple pendulum means there's a rigid support. From the support there is a string, and at the end of the string there is a bob. Okay. So slowly we are making the bob to move from one end. So what happens? It starts with moving with a natural movement or natural vibration. Okay. So the natural frequency of the bob or the simple pendulum depends upon the length of the pendulum. So it has to be taken from the point where it is supported till the edge of the bob. That is called the length of the pendulum. How can we find out the natural frequency? We have an equation, and two factors it depends. First one, the length of the pendulum, and that is inversely proportional and is directly proportional to the acceleration due to gravity. So we can find out the natural frequency of the pendulum by using the equation 1 by 2 pi into G by L. So G, we know that G is also a constant upon the Earth's surface. So a single factor that always depends upon the simple pendulum, natural frequency of the simple pendulum, that is length. So as the length increases, the frequency decreases. Okay. For example, consider that we have a simple pendulum with a length is equal to 100 centimeter or 1 meter. When we apply in this equation, we will get it as it always vibrate with a natural frequency of 0.5 Hertz. Okay. So this is simple pendulum. The movement of a simple pendulum is an example for natural vibration. Let us see the next one. Another example for natural vibration, we can consider a spring with a rod. So one end of the spring has to be fixed at one end on a rigid support, and another end we should have to hang a load. Okay, we should have to hang a load. So what's going to happen? Just consider this is the initial position of the spring. We know that if nothing is there, if there is no load connected, it will be in a fixed way, right? No. So once we connect the load, what's going to happen? It's going to elongate, right? No. So according to the weight of the load, that spring will elongate. So for this case, so slowly we just want to keep the load and we just want to leave it, so it start vibrating up and down. Okay, the spring start vibrating up and down. That also an example for natural vibration. Now here also it can create a frequency, right? No, so how can we find out the frequency from this one? For a spring, there is a constant of rigidness. Always we know that it's made up of some metal particle and all. So there will be a rigidity for this one. So always we are using a constant called K. It is called the rigid constant. Rigid constant. So this constant varies for each spring. For different spring, the constant will vary. Okay. So for a particular, or the equation is equal to F is equal to 1 by 2 pi K by M. Okay. So K is a constant of rigidity and M is the mass, this load. For a particular spring, if you are using M is equal to 10 kg, frequency will be something different. If it is M is equal to 5 kg, it varies. So as the mass varies, the frequency varies. Same way, just consider that we have a constant mass 10 kg. Okay, we have a constant mass 10 kg, but we are changing the spring. So as the spring constant varies, also the natural frequency or natural vibration varies for the spring. Okay, let's see the next example. Our next example is tuning fork. So when we stab the tuning fork against a rubber pad, we can hear the sound. It is like a longitudinal vibration. So the tuning fork make the sound, or the vibration will be in the form of longitudinal vibration, and when it reaches our ears, we can hear a single frequency. So during that time, the tuning fork vibrate with a single frequency, natural frequency. For a particular tuning fork, it can only vibrate with a single frequency. So because of that, we always call it as monotone. The monotone, for an example for monotone, we can always mention tuning fork, because if it is 212 or 252, that is the frequency range, means if you strike the tuning fork against the rubber pad or anywhere, it produces a frequency only with that particular range, 512, 326, whatever it is. Okay, so tuning fork is also another example which produces a natural frequency. Now we'll see another example as the flute. You know what is flute, right? So flute. So as in case of flute, you know that air column. What creates a vibration there? Air column. The sound is produced due to the vibration of air column. You might have noticed that in that flute there may be lots of holes, right? No, and the person who is always blowing that, always you might have noticed the movement of the fingers. What is that fingers are doing there? They are making, arranging the length of the air column. By using the fingers, the person is managing the length of the air column. So as the length of the air column varies, it creates different frequency of vibration. Okay, so the length of the vibration or the length of the air column can create or can change the frequency of natural vibration. For a flute, as it is air column, the frequency of the air column is always inversely proportional to the length of the air column. As the length increases, the frequency decreases. As the length decreases, the frequency increases. So by managing each note or each position of the fingers, the person who is blowing that, they can manage each note of the music. Same way in an organ pipe, by managing the length of the air column, like if the both end is open, it can create different modes of vibration. So that vibration for both end open one, both end open case, the frequency, the way how the frequency is produced, if you are representing in terms of ratio, it's like that. 1:2:3. The frequency, the mode of change in the frequency is always like 1:2:3. If we are using an organ with one end open and another end closed, one end open and another end closed, if you are using such kind of organ, the mode of vibration, the mode of frequency vibration produced will be in the form of 1:3:5. So this is the way how the frequency variation, the mode of frequency variation will be seen in the case of organ. If the both ends are open, it is 1:2:3. If both ends are, one end is open and another end is closed one, we will get in terms of 1:3:5. Another main example for producing natural vibration is the stringed instruments. Okay, we know that string instruments, there are few factors. In lower class also we studied how the frequency can be varied, right? Which are the factors depends for stringed instruments? Stringed instruments, for example, guitar, violin. We know that different strings are there. We know that there is a factor called length of the string, right? No, so the frequency is always inversely proportional to the length of the string for a stringed instruments. At the same time, the thickness of the string is also a factor which decides the frequency. So frequency is also inversely proportional to the radius. Thickness we always represent in terms of radius of the string. And another one more factor is that is the tension of the string, right? Now as the tension increases, the frequency can be varied. So here the frequency is directly proportional to the tension of the string. Now we are going to, so we have three factors. We will write down a single equation relating all these factors. So the natural frequency of a stringed instrument is equal to 1/2L into T divided by pi r square D. From where this D has come? Actually, D is the density of the material. Okay, D is the density of the material. And this pi r square D can be considered equal to the mass of the material for unit length. Per unit length. Do you have any confusion that how I can make or how I can write pi r square D, that is area into density is equal to mass? Do we study any connection with that? You know that density is equal to mass by volume, right? So volume for a material means area into length. Here area is here. So I can write it as m by pi r square. But length is missing, right? Now here it is mentioned that for unit length. So it is for 1. If unit length means the value is always 1. So in that way we can write m is equal to pi r square density. Here we are using the notation as D. So that is the way we can make it as pi r square D is equal to m. But you have to mention that for unit length. That is equal to the mass of the material per unit length. So this is the equation to find out natural frequency of a stringed instrument. Just now we saw the natural vibration or the frequency of a string instrument. Now consider a case that for a stretched string, just consider that we have two ends here. In between we just made a string to tie. Okay, stretched string. How it produces vibration? Okay, it also produces vibration, right? So just consider that you're going to pluck it exactly at the middle. It make a single knot of vibration. If you are plucking exactly at the middle, it make a single knot of vibration, or it make a single loop of vibration with a principal knot. If single is there, we used to consider it as principal knot. So frequency we used to consider it as F. Okay. If it is half, now you are going to pluck at 1/4. Okay, second one you are going to pluck it at here at exactly half. Here you are going to pluck it at 1/4 length. You will get two loops. instead of single loop, you will get two loops like this way. So here it's a secondary node, frequency will be equal to 2f. Here natural frequency is equal to f itself because it's a principal node. Second time when you pluck it 1/4 the length, you will get two complete loops. So the frequency is equal to 2f. Now if you are going to pluck it at 1/6 the length, you will get 3 complete loop. Okay, you will get 3 complete loop. So f will be equal to 3f. Okay. So if we represent this in terms of ratio, we can mention that for a stretched string, the frequency, the mode of frequency vibration produced, natural frequency vibration produced is equal to 1:2:3. Same way, if we consider in terms of wavelength, it is equal to 2L. This is 2L. For the second one, it is 2L/2. Third one, it is 2L/3. That is the way how the wavelength will be related. So if you are mentioning in terms of wavelength, it will be in the just reverse order. 3:2:1. So wavelength will be in terms of 3:2:1 and frequency will be in terms of 1:2:3 for a stretched string. Okay. Now if we consider the case of piano, by pressing different keys, it also connected to different strings, like how it is connected with a guitar and all. So depends upon the strings tension, depends upon the strings length, depends upon the area of cross section, the frequency will vary with the previous equation. So these are some of the examples of natural vibration in the absence of external force. Okay, in the absence of external force, we can consider all these examples, all these vibrations are producing the natural vibrations. Now we'll see the nature of natural vibration. So we can tell that the natural vibrations are somewhat similar like a simple harmonic motion. Simple harmonic motion means always the motion have equal displacement, or the amplitude will be equal for all the time. That is called simple harmonic motion in a simple way. Okay. So if you see the nature of the natural vibration, or we are presenting in terms of a graph, we can tell that natural vibrations are the vibration which are with constant amplitude. These are the vibration with constant amplitude and constant frequency. As the time goes on, it never varies the frequency or never varies the amplitude. Okay. So if you are mentioning time in x-axis and displacement in y-axis, we can mention like equal displacement. Okay. So always it should be of equal displacement. Just I am making a line over here to maintain the distance. Okay. So this is called natural nature of the natural frequency. Equal amplitude in either sides or equal displacement in either side. It never, or it always continues. It never varies the amplitude. That is the nature of natural vibration. And this natural vibration is only possible to occur in vacuum. If it is happens in the normal situation, the surrounding medium always make a resistive force and the energy loss will happen. Okay. So that is the reason it loses its energy, and automatically the amplitude, the vibration amplitude decreases. Okay. So that we used to consider as another category of vibration, that is called damped vibration. Okay. So damped vibration means all these examples what we studied, if it is happens in the normal condition, in atmospheric condition, we can call it as damped vibration. Damped vibration. So all these examples, if it happens in the normal condition, we used to call it as damped vibration. So we can represent damped vibration in terms of, or simply we can tell that it is a vibration with decreasing amplitude. Okay, it's a vibration with decreasing amplitude. T is in time is in the x-axis and displacement is in the y-axis. So this is the way how it is going to happen. Slowly it decreases the amplitude and finally that vibration will come to rest. Okay. So this is the way how we have to represent the damped vibration. Okay. So it's a vibration with decreasing amplitude. Like the normal swing, even the simple pendulum, the movement of this body. See, now it's moving with a maximum amplitude, and as the time goes on, what happens? Slowly decreasing its amplitude. So here the surrounding medium is having the air. Air is exerting a pressure on this one or exerting a force on this one, resistive force. That is a fluid friction. See, slowly the amplitude is decreasing and it comes to rest. Okay. Or you all people love to be in the swing. So what happened? Once the swing is moving, after that don't give any external force to that. So slowly what happens, if you are not giving any external force, initially it moves with maximum speed, then slowly the amplitude, the speed reduces and the movement, the displacement between the movement reduces and it comes to rest. Or if you pluck the tree, the branch of a tree, then you leave it, you can see it's vibrating, but very soon it will come to the rest position. Likewise, all the kind of vibration, or you just stretch a string and just make it into vibrate, slowly it comes to the rest position. After few vibrations, slowly it comes to the rest. So all the vibration, all the examples what we mentioned in the natural frequency or natural vibration, if it happens in the normal situation, normal surroundings, that is an example for damped vibration. All these examples we can see that initially when it's set into the vibration, it possesses maximum energy. So as the time goes on, due to this resistive force or resistive opposing force, it loses the energy. So we know that when we don't have much energy, we may not be able to do with the full-fledged, right? No, initially the body vibrates with maximum energy. Because of this resistive force, it loses the energy. So it may not have much energy to move with maximum displacement. That is what actually happens in the case of damped vibration. Let us move to the next kind of vibration, that is forced vibration. So forced vibration means when the body is set into vibration with the help of an external force. Okay, the body start vibrating with the help of an external force. That is what we call forced vibration. When a body is set into vibration, that forced vibration, it experiences three kinds of forces. First one, restoring force. Restoring force is happens with all the kind of forces like natural vibration, damped vibration, everywhere. The restoring force is there. That means when it moves from one position, it has to come back. That is called restoring force. So restoring force is common for all the kinds of vibration. Then second one is a resistive force. First one, restoring force. Second one, resistive force, where the resistive force acting in the normal situation, that is in the damped vibration due to the external surrounding. And the third one, here is a external forced vibration. Okay, external force, that is happens in the case of forced vibration. Normal case, the natural vibration, the body start vibrating with the restoring force. Then what happens with the damped vibration? The resistive force made to lose the energy. So slowly it loses its energy and automatically the amplitude will reduce, right? No? During that time, what's going to happen? We are going to give an external force. For example, the swing. We know that after a few vibration, just imagine that it's going to be die out. The moment is going to die out. By that time, another person is going to make a movement. They are going to push the person who is in the swing. So what's going to happen? It's going to vibrate again. Right? No? So slowly, when the external force is applied on the natural vibrating body or a damped vibrating body, it is going to lose that natural vibration. slowly it occurs a external vibration, the frequency of the external vibration. The natural frequency will dies out, and from that it switch into the external or the forced frequency. Okay, the forced vibrations frequency. And we used to call this external force with another name called driving force. Okay, driving force. If the external force frequency is different that of the natural frequency, the object is going to vibrate with a smaller amplitude. Another condition, if this external frequency is going to be equal with the natural frequency, the object will start vibrate with a bigger amplitude. Okay, if it is different, smaller amplitude. If it is equal, it is going to vibrate with a bigger amplitude. And we used to call that kind of wave as resonance. Okay, that condition we used to call it as resonance. That in detail we will see it in the next class. Now let us see some example for this forced vibration. For example, consider a vibrating tuning fork. Okay, a vibrating tuning fork means it's already having a vibration, and consider that as an external frequency, and we are going to keep it that on the tabletop. We know that the tabletop is having a large surface area. As the surface area is more, it produces louder note. So when we keep this external periodic force or external frequency, external vibration on this tabletop, the tabletop start vibrating with a louder note. Okay, so there the frequency. So this external force made that tabletop to vibrate with a forced vibration. Okay. Same way the microphone. We know that the speaker, when the speaker speaks something, the microphone will multiply it. So the speaker's sound is a external force which make the microphone to make a bigger sound. Same way the guitar, the hollow guitar, we know that under that it will be kept in a hollow space. It will be mounted on a hollow base, right? No? So the string is making the vibration, right? The string, what happens with the air column, inside that full air column is there, that this external force made by the string made that air column to vibrate. So as it is having a large area, it start producing a bigger sound or a louder sound. If you see the differences between natural vibration and forced vibration, the natural vibration always happens in the absence of external force. Forced vibration, it happens in the presence of external force. Okay, here absence, there presence. Okay, for natural vibration, the frequency is always depends upon the size and shape of the body. There the frequency depends upon the external force. Okay, so for natural frequency or natural vibration, the amplitude is a constant factor. There the amplitude varies according to the forced vibration. Last factor, the frequency of the free vibration is always constant for a particular material, and for the forced vibration, it depends upon the frequency of the external force which is applied. It always depends upon the frequency of the external force. So these are some of the examples and the differences between natural vibrations, free and the forced vibration. In between we are getting the damped vibration. When the damped vibration is there, we have to apply an external force. There we will get the forced vibration. We will see resonance in the next class. Thank you.